folks.
Morning.
All right, so last time we started talking about alkylides, and we started talking about the fact that these alkylides can undergo reactions. Right, so let's just take some sort of alkylide. Right, so it's an alkyl halide, happens to be iodine. What do we know about the leaving group ability as we go down the family? Is it better or worse as we go from top to bottom? Yeah, it gets better, right? So iodine's a really good leaving group. It likes to react with a variety of nucleophiles, right? Give me an example of a nucleophile that you learned about on Tuesday. What would be a nucleophile? Pardon?
Chlorine.
Chlorine can be a nucleophile. In this case, I don't want to use it though, because it's not a great nucleophile in the sense that it's going to give me, but I could use it, right? What's another example? Yeah, there were some nitrogen nucleophiles. Anybody remember what they were? Yeah, N3, or azide is what it's called, right? So N3 minus was a good nucleophile, and we learned that we could make carbon-nitrogen bonds doing this through what's called a substitution reaction, or a nucleophilic substitution reaction. This is the nucleophile, and this is the what? Nucleophiles react with electrophiles, right? So we have an electrophile. These are typically abbreviated as E+, even though there's no formal positive charge, it's just a generic. You'll see why later. And this is the nucleophile, which is generally represented as nu with a lone pair of electrons. You also learned a rule. What was that rule that I taught you? All nucleophiles are Lewis bases, but not all Lewis bases are nucleophiles. That's right. So this is a Lewis base because it has a lone pair of electrons. It's an electron pair donor. Happens to be negatively charged in this case, but that's okay, right? So if a nucleophile is a Lewis base, then what's an electrophile? A Lewis acid. That's exactly right. Right? All electrophiles are Lewis acids. And you might remember at the beginning of the semester I told you that the most important reaction in the world is the reactions of Lewis acids and Lewis bases with one another. But when you look at that, nothing up there suggests anything that you learned in general chemistry about acids and bases. You don't see sulfuric acid, you don't see hydrochloric acid, you don't see, right? But this is an electron pair donor, and so this must be an electron pair acceptor. Right? And so we took that concept on Tuesday and started thinking about what does that mean in terms of a mechanism. Right? And we came up with three possibilities in our little thought experiment. Right? The first possibility would be that the nucleophile reacts with the electrophile at the same time that the leaving group leaves. That was scenario one. We said that seems plausible. Right? The nucleophile can react at the carbon, the leaving group can leave, that all happens at the same time. And we said since both things would be going on at exactly the same time, that the rate of that reaction would be proportional to the concentration of the alkyl halide and the nucleophile. So if I increase the concentration of the nucleophile, I increase the rate. If I increase the concentration of the electrophile, I increase the rate. Okay, we talked a little bit about that. This is called a second order rate equation. Okay? So the rate of that reaction is going to be proportional to the concentration of the alkyl halide and the nucleophile. We said there was another possibility too. We said, why couldn't, or we proposed anyway, why couldn't the alkyl halide, in this case I'm going to use iodide again. I'm just going to put some things there because that's what's on the board. right? Why couldn't the halide leave first? Right? And then the nucleophile come in to make the bond, right? And we said that that was plausible, right? We could have this leave. We're not breaking any rules of octet. We know carbon can take on a carbocation. We've talked about carbocations before. I can't put it in a bottle, right? But they can exist that way for a little while. They're called intermediates, right? And we learned that the rate of this reaction should only be proportional to the concentration of the alkyl halide. Why doesn't the nucleophile come into the rate expression here? Pardon?
Because that's probably the second step, not the first.
That's true. What else? Let's do another thought experiment. Let's suppose that I have an old beat up car that doesn't run very well. And let's suppose that Alyssa has a brand new Corvette. And we are in downtown Hattiesburg and we're at the stoplight, right, on Main Street. And there's stoplight, right? Is she necessarily going to get to the end of that before I do? Bigger engine, better car, faster, but yet we'll end up probably getting to the end of Main Street at exactly the same time. Why is that? The stoplights. It's called the rate determining step. It doesn't matter that she's got 450 horsepower and I've only got 81. What matters is she's going to hit the gas, she's going to take off, and the next stoplight's going to stop her. And then I'm just going to crawl right up to it. And I'm going to sit there and look at her, and then next one, and she's going to take off, and I'm going to get right, and that's what's going to happen. And so this step is what we call the rate determining step. This is the old clunker car. This is the Corvette. Okay? The slowest thing to happen is breaking that bond. Does that make sense? I see a lot of heads nodding yes, but tell me, why does that make sense? Why does it make sense that breaking a bond should be slower than forming a bond?
Because it's harder to do.
Yeah, it takes more energy. Right? It takes a lot more energy for us to break a bond than it does to form a bond. We learned that all bond breaking events are endothermic. And we learned that all bond forming events are exothermic, right? Remember at the beginning of class, one that time during the start of the semester, I told you that you learn in biology wrong, that ATP, the bond breaks and you get energy. It's nonsense, right? Breaking bonds always takes energy. It's what happens with those pieces afterwards when they form new bonds that gives the energy. ATP is an energy source. I'm not saying you were lied to. I'm just saying it was oversimplified to you, okay? All bond breaking events require energy. Even the splitting of the atom. You know, when you do nuclear stuff and you break atoms in half, they say, oh, you get energy from breaking the atom in half. No, it's because you get more stable things that release the energy, not because you broke it in half. That takes energy. Okay? So we said this was plausible. Then we said there was a third possibility. Seemed plausible, right, that the nucleophile could attack the carbon, form these 5 bonds around carbon, and then the leaving group can leave. And we excluded this as a possibility in organic chemistry. And why is that? That's right. The octet rule, right? It would be very difficult to have 5 real bonds around carbon. Why is that? Because carbon is in the second period. It has 1 2s orbital and 3 2p orbitals. It can handle how many electrons? 8. There's no room to put those 2 other electrons. The hotel is full, right? So it just doesn't make any sense for the mechanism 3 to even be plausible, at least in organic chemistry. Okay? There are other elements that will do this kind of chemistry. The carbon doesn't. Okay? So, that's where we stopped. So, let's talk about that first reaction, where the alkyl halide reacts with the nucleophile. And we can show this like this. Right? We can do that. Now here's the mechanism shown in an energy diagram. Okay? You might remember these types of things from general chemistry. Here's our starting materials. Here's our alkyl halide. Here's our nucleophile. Right? They're at this energy. The reaction occurs. We go through, what do we call this? It's a transition state, right? It's the highest energy. Notice, this is the energy of activation. That's how much energy it takes to get to the transition state, right? What kind of looks weird about the transition state? Compared to what I just drew here with the arrows. What looks weird? There's partial bonds. Yeah. Right? If you look at everything, you should have been asking me, hey, whoa, wait a second. There's 5 things around that carbon. Yeah, but I can cheat and I can use dash lines. And now you're going to say, well, isn't that convenient? Right? That you get to use dash lines. You get to cheat a little bit. I'm really not cheating. I told you you can't have 5 real bonds around carbon. And that's true. But I don't have 5 real bonds around carbon right now. How many real bonds do I have around carbon at the transition state? I have 3. Bromine is leaving at the same time that the nucleophile is making its bond. So those are 2 partial bonds. Let's just say they're half bonds, right? So that's a total of 4. How can I get away with that? What else do you see about that transition state that makes you kind of go, There are partial charges, right? So my nucleophile is negatively charged, and as that reacts, that negative charge is going to diminish, right? Because I'm forming a bond. In the starting material, my bromide doesn't have any charge on it, but as it starts to leave and takes those electrons with it, it's going to start to build up a negative charge, right? So we have these charges that are starting to change. What else? What can you tell me about the relationship of the leaving group and the nucleophile? If you were in a math class and you had a protractor, what would you tell me? Where is the nucleophile relative to the leaving group? You mentioned protractor. What's a protractor do? Measures an angle, right? So if I have this carbon, and let's draw this out kind of like they have it. Something like that, right? I think that's the right one, right? So we have a partial negative here, negative here. And this double dagger means the transition state. That's what that means. And they put it in brackets. What does that mean? It tells me it doesn't really exist. I can't put it in a bottle. It's fleeting. Okay? It's a fleeting thing. Can't observe it too easily. So if you got a protractor out and you laid it up here, what would you tell me about the nucleophile and the electrophile? They have to be what with respect to one another? 180 degrees, right? The angle here is a straight line. That's 180 degrees. In other words, the nucleophile is attacking the carbon. By the way, organic chemistry is a very violent sport. You'll hear me say attacking all the time, okay? And that's the correct terminology. So the nucleophile attacks the carbon, which is the nucleus, right? And the leaving group is leaving, and this has to be 180 degrees. Why does that have to be 180 degrees?
So that they don't interact with each other.
That is the very first thing you should observe. Yes, that is true. They don't interact with each other. Why would that be a bad thing? What does bromine have on it that we didn't draw? It doesn't have a charge, but it has things that are charged. Those lone pairs of electrons, right? There's lone pairs of electrons. So bromine has lone pairs of electrons around it. What does this oxygen have on it that I didn't draw? Lone pairs of electrons as well. Are they going to want to get close to one another? No, so what's the furthest that they can be? 180 degrees. That observation explains everything, but it's only half true. It's not wrong. It's only half true. Right? The electrons have to go somewhere. Where do electrons go? What things do we say that house electrons? What do we call those things?
Orbitals.
Orbitals, right. Now wait a second. I'm not going to make you draw the orbitals. I just want you to understand this, okay? Every time you see a bond drawn out, that's an orbital. That's where electrons are. That's what a bond is. It's nothing more than an orbital. Okay? So, in the starting material, there is a bonding orbital between this carbon and this bromine. I think everybody will agree with that. That's why we call it a bond. But I can have bonding orbitals, and I can have what other kind of orbitals that you might have learned in Gen Chem? I can have anti-bonding orbitals. Anybody remember what those were? Those were orbitals that if you put electrons in, it broke bonds. So you might remember when you did the hydrogen diagram in Gen Chem, just the two hydrogens, the two electrons went into the bonding orbital at the bottom, and then the anti-bonding orbital was left alone. And you probably explained, well, if you add a couple more electrons to that anti-bonding orbital, hydrogen should break apart, and in fact it does. Right? Where do you think this nucleophile is attacking? It's attacking the anti-bonding orbital for this bond. And that happens to be on the opposite side of the leaving group. Got to have a place to put the electrons, so the nucleophile attacks that anti-bonding orbital. The leaving group leaves, and you end up with the product. Okay? These orbitals can rehybridize. The anti-bonding orbital eventually becomes a new bonding orbital. Okay? And I know that sounds confusing. It's one of those things you're going to have to trust me on. What you need to know is that the nucleophile in this reaction attacks from the backside. It's called backside attack. Okay? And I can prove that it attacks from the backside using some chemistry that we learned in chapter 6. Okay? So, let's see what we can figure out from that. Let's suppose we take a molecule that looks like this. Carbon, there's my carbon, there's my halogen, there's some other carbon group here. Let's just think it's a methyl group. Let's make it simple. I have a deuterium, which is a heavy hydrogen, and I have a hydrogen. What is unique about this carbon now? How many unique things does it have around it? 4. So it must be chiral. It is a chiral molecule. It's a chiral alkyl halide. So, assign the stereochemistry to it for me. How would we assign the stereochemistry? Is it R or is it S? It is S. How did you determine that? Okay, so the bromine is number 1. Yeah?
Yeah, hydrogen is low, so I was 4.
That's right. And it's already away from us. That's convenient, isn't it?
Yeah.
So, yeah, and so now we have to make a decision between whatever that carbon group is on for R and deuterium. And deuterium is just hydrogen, just heavier, right? So it's going to be the lowest priority of those 3. Right? So 1, 2, 3, you're right. It's going to be S. Now, if this reaction occurs through this mechanism where the nucleophile attacks from the back and the leaving group leaves, you're going to end up with a molecule with that configuration, right? Because the transition state goes through this kind of planar arrangement of the R, H, and D, and then as this new bond is formed, those things pop back out. It's kind of like the inversion of an umbrella. What is the stereochemistry of the product now? Assuming that the nucleophile has a higher priority than carbon. Let's make that assumption, okay? What is it now? It is R. It has gone through inversion of stereochemistry, okay? And we can do this experiment and show that the kinetics are dependent on the concentration of the nucleophile and the concentration of the alkyl halide. And I can start the reaction off in a polarimeter tube and I can measure how the polarimetry changes, how it rotates plane polarized light. It will 100% invert the stereochemistry of that reaction. If I have S to start with, I will have R in the product, 100%. Okay? This is called inversion of configuration. Okay? And that's how we prove that this occurs. This is called an SN2 reaction. What does the S stand for? Substitution. What does the N stand for? Nucleophilic. What does the 2 mean? It means it's second order. It's a second order reaction. The reaction is dependent on the concentration of the nucleophile and the alkyl halide. That's what the 2 means. Substitution, nucleophilic, second order, or bimolecular, some people call it. Okay? This happens. How many steps are there for this reaction? As it's drawn, how many real steps are there? There's only really one. The nucleophile comes in from the back at the same, remember everything's happening at the same time, there are no intermediates. Right? I mean, there are 3 things that you're looking at, but it's one step. Okay? SN2 reactions are one-step reactions. You got to keep that in mind. Here's some examples of SN2 reactions to things that you all might be particularly interested in. You can take this amino alcohol, so you got an amine and an alcohol group, and you can react it with this 1,2-dichloroethane. You just have to have 2 equivalents of this and 1 equivalent of that. And you can make this medicine called ethambutol, myambutol. Okay, these are used for people, I believe these are inhaler kind of molecules to help open your airways. It is made by nothing more than what you have learned in this class. It's just made in a big lab, on a big scale, with people who are qualified and people who can make sure that there's no poisons in it when they package it, right? But you could go into my laboratory right now and make ethambutol very, very easily. Okay? This is another example of a good SN2 reaction. This alkyl halide, this alkyl iodide reacting with methylamine to form this nice carbon-nitrogen bond. This is a one-step reaction. Okay, or this is a one-step reaction, and then another step is used to make, ultimately, Prozac. Prozac is made by the chemistry that you all are learning right now. It is just an SN2 reaction to give you the carbon-nitrogen bond that you need. And interestingly enough, when you look at Prozac, it kind of looks like methamphetamine a little bit. Has similar structures to methamphetamine. Okay? Makes sense, right? Both are psychoactive drugs. One's beneficial, the other is not. But nonetheless, they share similar structure. Okay? There's only so many ways that you can interact with a brain cell. And you'll find that these types of functional groups appear over and over again. All right? Here's another example of an SN2 reaction that you all might have made use of. If you have ever been in a situation where you have gotten scared, really scared of, for your life, or, just somebody really scared the living daylights out of you, what happens to you? You start to form adrenaline, and your heart rate starts to go up, and your breathing starts to change, and your eyesight gets a little different, right? You get into fight or flight mode, right? We all know about that. This is nothing more than the biology of your body doing an SN2 reaction. You can't be in that state all the time. You would die, right? You would wear yourself out really quick. The only problem is your body can't use alkyl halides. They're toxic. It will kill you. But biology has been clever and has come around with a way to make what is the equivalent of biological bromide. It's this.
So is this for allergic reactions?
Pardon?
Is this used in allergic reactions?
Could be, yeah. I'm not an expert on the medicine, so can't comment too much. But this is called SAM, S-adenosylmethionine, and it is the biology equivalent, essentially, of bromomethane. But your body can't make bromomethane. If it did, you'd die. But it can make SAM. This is the leaving group. Man, that's a big leaving group, right? But a nucleophile can react with SAM just like it can an alkyl halide, and it attacks the carbon, and the leaving group leaves, and you form a new carbon nucleophile bond. And this turns out to be very important in the formation of adrenaline. You can't have adrenaline all the time. You would wear out. You'd age really quickly, and you'd die in a couple of days, right? Probably. But you sense some sort of stress, danger, right? A nerve signal gets sent from your brain right outside the kidney. There's this thing called the adrenal gland. And what it has is it has this molecule called noradrenaline or norepinephrine. It is not adrenaline yet. It does not have that methyl group on the nitrogen, right? This is relatively inactive. This is the active molecule that gives you increased heart rates, yada, 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 right? Again, kind of looks similar to methamphetamine, right? But what happens is your body releases this, it reacts with SAM, it gets methylated, and it triggers the response. So your brain can control the adrenal gland about what it does in terms of releasing the noradrenaline. Nothing more than an SN2 reaction. Okay, but it's a biologically important. All right. That's the SN2 reaction. Let's talk a little bit about the SN1 reaction. The SN1 reaction is the reaction that is substitution, nucleophilic, unimolecular. One. The only thing that matters is the formation of the carbocation and the rate. So here we've got an example where we're taking tert-butyl bromide, right? That's the name of the alkyl halide, and we're going to react that with some sort of nucleophile. And so when we put these things in solution, what happens is the bromine has to first leave. When the bromine leaves, I get a carbocation, right? So that's the first phase of the reaction. And then the nucleophile, in this case we're using this acetate again, will simply come in and react with the alkyl or the carbocation and form the new bond. This is the slow step, this is the rate determining step, so this is the only thing that appears in the rate equation, right? So Melissa comes to lab, she wants this to speed up, so she adds more acetate, and then she gets disappointed because she realizes she added more of the wrong thing. You can add all the acetate you want, it's not going to increase the reaction rate, okay? It's not part of the step. Right? If she wants the reaction to speed up, she needs to increase the concentration of the alkyl halide, right? This is what the energy diagram for that looks like. How many steps does this one have? Two. It's SN1, but it's 2 steps. You gotta kind of keep that straight, okay? So what happens in the slowest step? How do I know this is the slowest step? It takes the most energy. It has the highest energy of activation, right? I look at the second reaction, which is the reaction of the carbocation with the nucleophile. It's got a very small energy of activation, relatively speaking, right? So the first step happens, The leaving group leaves, I get a carbocation. That carbocation then readily reacts with a nucleophile, and I get my product, okay? This is the SN1 reaction. I will tell you, for the next exam, you need to have these reaction energy diagrams in your notes. There will be questions about the differences between an SN1 reaction and an SN2 reaction, okay? Let's skip that for now. So, how in the world do we know that this is true? We can use the same experiment that we did before, except now we're starting off with this chiral alkyl halide, right? I've got this ethyl group, I've got a methyl group, and then I've got another methyl group that has one of the hydrogens replaced with deuterium. So there are 4 different things around that carbon. We're not going to worry about whether it's R or S, just know that it's enantiomerically pure. It's just one molecule. We put it in the presence of the nucleophile, and we let the reaction occur. And what we find is that when the leaving group leaves, I get a planar carbocation. It's planar. Those 3 groups, there's the plane, right? It's planar. The nucleophile has equal opportunity to either attack from the front or the back, because it's a p orbital. It can come from the front or the back. What are the odds of it coming from the front or the back? 50-50. Remember, these things don't have brains. They don't pick a side, right? It's just statistical mechanics. Well, it can attack from the front, it can attack from the back. There's no reason to prefer one over the other, so it ends up being 50-50, okay? And in doing that, what do I end up with? What are B and C with respect to one another? They are enantiomers. And if they're there in 50-50 mix, what do we end up with? And what do we know about racemic mixtures? Do they rotate plane polarized light? They do not. So, we put this in a polarimeter tube. We're watching the rotation of the plane polarized light. We let the reaction occur, and what we find at the end of the reaction is that the plane of polarized light doesn't rotate anymore. Okay? We have a racemic mixture. So, what does this mean for you if you got a job in chemical industry? It would mean you lost your job. Why would you lose your job? Because chiral molecules that are enantiomerically pure are expensive, and you just set up a reaction that takes an expensive starting material and makes a very cheap product. That is a guaranteed loser in any business model. Okay? A casino cannot give out more money than it takes in, or it goes bankrupt. A chemical company cannot spend more money than it takes in, or it will go bankrupt, right? And that's what would happen here. We'd have to spend a lot of money to buy this, and we couldn't charge very much for that. Your boss would come down and fire you, okay? It's not a good business model, okay? So, we're going to try our best to finish up. And that should, I guess I didn't change the old title. It's not chapter 6:13, this is the last part of 7. Okay, so, right, we just talked about this, so I'm not going to do much of that. I know that that has to be an SN1 reaction because it goes through a carbocation intermediate. What else should I be cautious about if something goes through a carbocation intermediate?
If it's going to form a reaction that you don't want to occur.
True, it can rearrange, can't it? Remember, anytime we form a carbocation, they can rearrange. We talked a little bit about that when we talked about the addition of like HX to an alkene, right? You form a carbocation intermediate. That can all go haywire because you have a carbocation intermediate. That tells us something about carbocations. They're intermediates, but they're not stable, and they will rearrange to things that are more stable. So one has to be careful about that, right? And it turns out that not all carbocations are equally stable, okay? So if I have a primary alkyl halide, or a methyl, a primary, a secondary, and a tertiary, I notice that as I do SN1 chemistry on them, that the tertiary alkyl halides and the secondary alkyl halides will react. Tertiary very, very quickly. Secondary a little slower. Primary, they don't do SN1 chemistry. And the methyl halides don't do SN1 chemistry. These things like to do SN2 chemistry. So methyl halides and primary alkyl halides do SN2. Secondary and tertiary like to do SN1. Okay? Secondary is a little more complicated than that, but anyway. Why do you suppose a tertiary alkyl halide will do SN1 chemistry, whereas a primary won't? What do you suppose? What must that mean about the tertiary alkyl halide? The carbocation that it generates must be what? If something's reacting fast, is it going to have a high energy barrier or a lower energy barrier? Lower energy barrier, right? So that must mean that it's easier to form a tertiary carbocation than a primary carbocation. Well, that's interesting. What about the number of carbons that are attached to that carbon make a difference? Right? Well, here's some things just to refresh our memory. We know that the rate of this reaction, an SN1 reaction, is only going to be dependent on the concentration of the alkyl halide. We know it's going to be 2 steps. We know it's going to have a carbocation intermediate. And we know from looking at all these experiments that the more substituted the halogen, the faster it reacts. We know that a tertiary alkyl halide is faster than a secondary, and so on. Therefore, I must know that a tertiary carbocation is more stable than a secondary carbocation, is more stable than a primary carbocation, is more stable than a methyl carbocation. The more carbons you have around that carbocation, the more stable it becomes. Those carbons are donating a little bit of electrons, if you will, to the carbocation to help stabilize it. Okay? And we can see that in these plots. Okay? The more blue that you see on the carbon atom, the more positive it is, the more positive charge. There's a lot of blue on a methyl carbocation. There's quite a bit of blue on a primary carbocation. There's quite a bit of blue still on a secondary carbocation, but your tertiary carbocations, not so blue. Yes, they're formally positively charged, but these other groups that are around it help stabilize it, help shield it a little bit, if you will. Okay? And so, for all practical purposes, the only carbocations, at least for this class, that you can generate are secondary and tertiary. So if you have a secondary alkyl halide or a tertiary alkyl halide, you need to be thinking it might do SN1 chemistry. Okay? It turns out, oh gosh, it's been over 50 years ago probably now, but you never want to tell a chemist, especially one with a big ego, that something can't be done, right? And there was this gentleman named George Olaw and Herb Brown. They competed with each other. One was in California, one was in Indiana. And they had these big arguments for years. Both of them went on to win Nobel Prizes in this area, oddly enough, because they did what nobody thought could be done. George Olaw was able to prove you can make methyl carbocations, but you have to have this nasty concoction of stuff called magic acid. And it is magic because it messes with your head in the sense of how it works. But it takes so much energy to do it. It's just not. But you never tell a chemist it can't be done. They'll find a way to do it, right? So even though it technically can be done, for all practical purposes, you're limited to the secondary and tertiary carbocation. Okay? So why is it that a carbocation that has substituents, why are they more stable than carbocations that do not? So here's an example of the methyl carbocation. And what you can see, of course, the positive charge is on this carbon. Here's the p orbital, so it's sp2 hybridized, right? It's an sp2 hybridized carbon atom, even though it doesn't have any double bonds. But it's flat and it's got a lone p orbital. No electrons in the p orbital. And notice where the hydrogens are. Where are they? They're in a plane. Where is that plane going through? It's going right through the center of where this p orbital is, right? And remember, the p orbital, I can have electrons here, I can have electrons here, but where can I have electrons there? No, I cannot. So the electrons in these carbon-hydrogen bonds can't possibly get into the p orbital at all. Okay, we call that orthogonal. It just means 90 degrees. Okay? But when I put a substituent out there, right? Notice now I still got the p orbital, but now I've got this orbital that has this carbon-hydrogen bond. It starts to touch that p orbital a little bit. I know that's a bad drawing. And when orbitals touch, what does that mean? Kind of bonding, right? So there's a little bit of bonding. We call this hyperconjugation. Don't worry about what that means. But essentially what can happen is some of the electron density from this bond can find its way to the carbocation. And if I take electrons and I put them in something positively charged, is that a good thing or a bad thing? It's a good thing. It lowers the energy. Now imagine I've got 2 things around it. That can happen more. If I have 3 things around it, that can happen even more. Right? So the more substituents I have around the carbocation, the more stable it is. And we call this hyperconjugation. Okay? And it's kind of weird because you can't really draw resonance structures for it without breaking the rules. But we know it has to be true because we see this difference in reaction rates. All right, so we just talked about that. We can move away from the Hammond postulate. Don't worry about the Hammond postulate. I'm not going to test you on the Hammond postulate. So we would expect then that the rate of an SN1 reaction would be dependent on the type of alkyl halide we had, right? The nucleophile does matter to some degree in both SN1 and SN2. It matters in the sense, not so much in terms of the reaction rate for the SN1, but it does matter in terms of whether or not something's going to go through an SN1 reaction or an SN2 reaction. Okay, so there are really strong nucleophiles and there are weaker nucleophiles. And it turns out that strong nucleophiles like to do SN2 chemistry, whereas weak nucleophiles really need to do the SN1 chemistry. Okay, we'll learn a little bit about that. So if we have 2 nucleophiles that have the same nucleophilic atom, the stronger base is almost always the stronger nucleophile. So for example, if I have hydroxide and acetate, both of those have a negatively charged oxygen. Okay, it turns out that the pKa, right, for hydroxide is 15.7 and the pKa for acetate is 4.8. And so since hydroxide is the stronger base, it's going to be the better nucleophile. Going to be the better nucleophile. What do I mean by the stronger nucleophile? Does that mean it forms a more stable product? Or does that mean that the reaction goes faster?
The reaction goes faster?
It could be both, but in reality it means that the reaction is going to go faster. So if I have a really strong nucleophile reacting with an alkyl halide, that reaction is going to occur faster than if I have a weak nucleophile. Okay, so the reaction rates will be different. Okay? Almost always a negatively charged nucleophile is going to be stronger than its conjugate acid. Water can function as a nucleophile in an SN1 reaction, but not an SN2 reaction. Hydroxide can function as a nucleophile in an SN2 reaction. Okay? And so hydroxide, being the stronger base, is going to be the better nucleophile. Okay? And we know as we go from right to left in the periodic table, in a period, we go up in basicity. And so this is a poor nucleophile, this is a better nucleophile, this is a better nucleophile, that's a really good nucleophile. So as you go from right to left, it's kind of the opposite of what we been learning in terms of our periodic trends. Okay, so fluoride is a worse nucleophile than hydroxide. Hydroxide is a worse nucleophile than amide, and amide is a worse nucleophile than the methyl anide. Okay? So, with that in play, I want you all to get together and I want you to figure out what's going on here. What's going to be the major product and what's going to be the minor product. This is called a competition experiment. What does competition mean? Fundamentally, when you all hear competition, what do you think? Winner and loser, right? We like winners and well, everybody likes to be a winner, right? But not everybody can be a winner, right? It's one of the things you learn playing t-ball. But, so here we're taking this alkyl halide. How would we name that alkyl halide? Yep, bromocyclohexane. And we're going to put it in solution with equal amounts of sodium hydroxide and sodium acetate. Both oxygen, negatively charged, both nucleophiles. And I want you to tell me which one is going to be, and draw the major product and the minor product. Take 2 minutes, work with your neighbors if you want. All right, folks, which nucleophile is going to win? Which one is the stronger nucleophile? Sodium hydroxide or sodium acetate? Sodium hydroxide. We know that that's going to be the stronger nucleophile, right? So the major product is going to be, in this case, what's the product? What functional group do we have? We have an alcohol. We converted an alkyl halide to an alcohol. And the minor product then is going to be this functional group, which we call a what? Does anybody remember? That one's called an ester. It's an ester. So we can react an alkyl halide with sodium acetate and we can make an ester. Okay? Major product, minor product. That would be fair game on the next exam. I do not expect you to know that it's 10-to-1 ratio or 100-to-1 ratio or anything like that. That requires a lot more chemistry, a lot more math, a lot more theory, right? But you should be able to look at a competition experiment like this and use your table of nucleophiles and tell me which one's going to be the major product, okay? So in these slides, there are a list of good nucleophiles and poor nucleophiles, and there is a list in your book as well, okay? So that would be fair game. Solvent also plays a role. You all go into the lab and you take chemicals and you put them in solvent, you dissolve them, and you largely ignore the solvent. But the solvent's important. It's not just a spectator sitting around. It participates, okay? And it turns out that we're going to learn about a couple different types of solvents. We're going to learn about polar protic, and we're going to learn about polar aprotic solvents, okay? You'll learn about those terms here. Now, if we take sodium bromide, I think you all will agree that's just a regular salt. It's like table salt, except it's got bromine instead of chlorine. And I think you all will agree that it will dissolve in water. Most sodium salts will dissolve in water. You learned that in general chemistry. Why does it dissolve in water?
On hydrogen.
Yeah, we're gonna start forming some hydrogen bonds. Yeah, you probably learned a little bit about that in Gen Chem. But if you think about it, if I've got sodium bromide all together, it's really just bonds between the sodium and the bromine, right? And there's multiple ones, you know, because there's a lattice, and you learned about that in Gen Chem. And we're going to ignore that for this argument. But we know that it readily dissolves, so it must be a favorable process, right? The solution must be more stable than the starting solid, right? Why is it more stable? Well, as Alyssa said, it's because of all these new bonds we formed. Right? Well, you think about sodium being positively charged things want electrons. Where can it get electrons? From the oxygens of the water. There's lone pairs of electrons. And so the water forms these bonds around the sodium. And what do we know about bond-making events? Good or bad? Good. So I just made a bunch of bonds with something. So that should be a good thing, right? And bromine can form bonds with the hydrogen atom because those hydrogen atoms are partially positively charged, right? Oxygen's pulling electrons to itself, and so they're going to. This is called solvation. This is what happens when you dissolve something in water. Water coats it. That's what makes it soluble, okay? We largely ignore this, except for the fact that we notice when we run a reaction in water, that reaction may or may not be faster than if we run it in another solvent. We see a solvent effect, right? So if I run a reaction in water and I get a particular rate, then I can run it in something that doesn't have the OHs. And I see that the rate changes, right? So let's say bromide's going to be our nucleophile here. This nucleophile is going to react with our electrophile. What's the problem? So let's say I've got an alkyl chloride, and I'm going to react that with sodium bromide, and I'm going to do this in water, and I'm hoping to get this. What's the problem with that reaction, right? I want my nucleophile to attack and my halogen to leave. What's the problem? What am I not taking into account here? It's not now, it's in solution. So let's assume it's in solution, but what am I not taking into account here? I'm not taking into account all those waters, right? What are those waters doing? Pardon?
They're surrounding it.
They're surrounding it. They are the bromide's clothes. So, if all of these waters come along and hit this atom, is the nucleophile going to be able to touch? No. Somehow all that water has to get removed before it can actually react, right? Is that going to speed up the reaction or slow it down? It's going to slow it down quite a bit. We typically see these types of reactions slow down in solvents like water because the water or water-like molecule like alcohols will solvate the nucleophile. It gets in the way. It won't allow the electrons from the halogen to react at the carbon. Okay? And so these waters get in the way and slow the reaction down, just like putting something in the way of anything slows it down. Okay? So that's kind of a bad thing. Okay? And it turns out that water and alcohols, we call those polar protic solvents. So let me draw water for you. Why is this, do we call this polar protic? Why is this a polar protic solvent? Let's break that down. Why is it polar? We have polar bonds. Oxygen is more electronegative than hydrogen, right? So we have a dipole that goes like this, right? Which means we have a dipole overall that looks like that. Right, so it's polar, yeah, that's easy enough. Got polar bonds and overall it's polar. What does protic mean? What does proto sound like? Sounds like proton. Hydrogens are also called protons, right? Because they have one proton, so they typically get called protons, okay? It is a polar protic solvent because it has hydrogen atoms attached to the electronegative atom. So, alcohols are polar protic. Things like alcohols are polar protic because they have the proton attached to the electronegative atom. And when you take the halogens and you dissolve them in water, for example, fluoride takes on a lot of water. Iodide takes on less water. It's bigger, it's less negatively charged per unit of area, yada, yada, yada. Fluoride gets very well solvated, iodide not so much. So which one's going to react faster? The one with a lot of clothes on it or the one with very few clothes? And by the way, in organic chemistry, we do call that naked. Again, organic chemistry was largely invented by men. So that's where it comes from, okay? I mean, no disrespect by that. It's just historically, factually true. But you can see the analogy, right? I mean, it's like putting a coat on and another coat. You've got all this clothing on there. It's going to be hard for a reaction to take place, okay? But there are another class of solvents called polar aprotic solvents. Notice in all of these cases, these are some examples. You need to memorize everything but HMPA. You need to memorize those. Those are all polar aprotic solvents that we'll be talking about throughout the semester. Acetone, fingernail polish remover. That's the main component of fingernail polish remover, okay? Or at least some fingernail polish removers. It is a polar aprotic solvent. Wait a second, but it's got hydrogens. Why is it aprotic? What did I say about polar protic? The hydrogen had to be attached to what? An electronegative atom. Is carbon, would we consider that an electronegative atom? No, not really. Right? And what you see is that in all these cases there are hydrogens, but none of them are attached to the oxygens or the nitrogens. Okay? So acetone is a good example of a polar aprotic. Acetonitrile, tetrahydrofuran, dimethyl sulfoxide, dimethylformamide. These are all examples of polar aprotic solvents that we use in our laboratory. Some of you may even use DMSO. If you use some creams, they use DMSO as a polar aprotic solvent to help deliver medication through your skin. So some of these patches and things will have a little bit of DMSO in them as well. So you're familiar with some of these molecules. Okay. Now, if I take something like sodium bromide, which will dissolve in acetone to a degree, and I place it in acetone, what looks different about this scenario versus this scenario? So look at the bromide here, and then look at the bromide here. What can you tell me?
They exist further away from each other.
Yeah, the solvent is there, but it's further away, isn't it? And if you also look at it, it looks like there's fewer solvent molecules around each halogen, right? So this halogen, the bromide in this case, is less clothed. So if Alyssa ran the reaction that I've got up here in water, and then again ran the reaction in acetone, which one would go faster? In the acetone. And so you're going to find that SN2 reactions typically react better in polar aprotic solvents. The solvent has an effect. The product's exactly the same, but the rate at which the reaction occurs is very different. And so it turns out that it's exactly the opposite when you're talking about polar aprotic solvents. Fluoride is actually a pretty good nucleophile in things like acetone, whereas iodide is a little less good. So the trends reverse. Okay? Now, I want you all to read this slide, and I want you to take a stab at what you think the products of these two reactions are. This isn't a competition reaction. This is a reaction that's run with a strong nucleophile in one flask and a reaction that is run with a weak nucleophile in the other flask. Take a moment. What do you think's going to happen?
I think it's gonna be an SN2 reaction.
Which one? Which one?
Oh, I'm sorry, I think OH will attach.
In an SN2 reaction? Okay, it will. Same thing will happen with water. I'll get the same product in both of them, except how they look. Both of them are going to be alcohols. Now, as Alyssa said, this is a strong nucleophile, so it's going to be an SN2 reaction, right? What's going to happen at this carbon atom if it's an SN2 reaction? Is the OH going to be solid wedge facing me, or is it going to be dash wedge behind me? It's going to be from behind, because it's going to come in from the back, right? What do you think is going to happen with the water as the nucleophile? It says here that weak nucleophiles tend to favor SN1 reactions. So what's going to happen now? What's the difference?
It's 2 steps instead
It's 2 steps. It means I got a, what kind of intermediate?
of
I got a carbocation intermediate in the second one, right? And so, yeah, it's exactly as you would expect, right? So this methyl group and this bromine are cis to one another. I react it with a strong nucleophile. It goes through an SN2 reaction, and now I end up with the OH and the methyl group being trans to one another, as you would expect, just as she described. But when I do this with a weaker nucleophile like water, the weak nucleophile can't just come in and kick the leaving group out. It's weak. It's not strong enough to do that. So what it has to do is it has to sit around and wait for the bromine to leave, or the bromide to leave a little bit. And when it leaves, I get a carbocation. Now, the oxygen of water can either attack from the top and give me the cis isomer, or it can attack from the bottom and give me the trans isomer. So I end up with 2 products, and these 2 products, are they going to be equal or unequal? Equal is what you should have answered. Yeah. Turns out they both form, they don't form in equal amounts, because cis and trans are not mirror images of one another. They don't have to have the same properties. They don't go through exactly the same transition state, oddly enough. Okay? But for the purposes of this class, if you said equal, that's good. That works. You recognize that it can attack from either the top or the bottom. But attacking the carbocation from the top here is different than attacking the carbocation from the bottom. And why is that? Because this methyl group is pointing out. So if the nucleophile comes in from the same side as this, it runs into it. And so I would expect to have a little bit of this form and a lot more of it coming in from the back. Okay? So that can happen when you have things that don't give you exactly the same molecule. Okay? We'll skip that. So, you all are going to need to be able to predict on an exam whether or not a mechanism is going to be SN1 or SN2. Okay? So, you need to know, strong nucleophiles favor what? SN2. Weak nucleophiles favor SN1. Tertiary alkyl halides favor SN1. Primary alkyl halides favor SN2, right? And you also need to keep in mind the nature of the solvent. So polar protic solvents are going to favor SN1. Polar aprotic solvents are going to favor SN2. Okay? So what would be fair game? I could give you a starting material or set of materials. I can give you a product and I can ask you, if I did this in acetone, would this most likely be an SN1 or an SN2? If I did this, and I can do any number of combinations, but you need to be able to predict based on the information that you're given whether or not something is going to occur through an SN1 or an SN2 reaction. Okay? So here's a list of nucleophiles. I told you that there were several. You need to have these kind of memorized. Okay, even though the R's can always be different, but focus on the nucleophilic atom, right? So we have oxygen-containing nucleophiles. I can react those with alkyl halides, and I can make things like alcohols, ethers, and esters. I can have these carbon-containing nucleophiles where carbon has a negative charge, and I can form things like nitriles and alkynes. I can have nitrogen-containing nucleophiles like N3- called azide or ammonia, and I can form azides and amines. And then I can have sulfur-containing nucleophiles, and I can make thiols and sulfides. Okay? So you can get all of these types of products. So if I was comparing these nucleophiles with one another, which ones do you think would be, they're all fairly strong, but which one would be the strongest, do you think?
The oxygen.
Oxygen's not bad, but it's not the best. It turns out that the sulfur, negatively charged sulfur, is called a supernucleophile. And it's because it's actually a little further down on the periodic table, like our family, right? And since we would have to be, since this is SN2, we assume that we're in polar aprotic solvents, right? So we would know that the sulfur would actually be the strongest nucleophile in this whole series, okay? All right, so I don't have too many slides left, but I'm not going to get into this before spring break. We'll pick up with this. So when you get back from spring break, we'll finish up chapter 7, get started in chapter 8. Let me just give you, I know you all are looking forward to enjoying your spring break. I'm looking forward to it myself. But what I would encourage you to do is spend a little bit of time making sure you remember your functional groups. Flip through your notes a few times. You don't want to come back from spring break cold. Our next exam will be at the end of March, and you don't want to have a week of just stuff getting stale. I'm not saying don't go enjoy yourself. Certainly do. But spend just a little bit of time staying refreshed. You'll find that makes a big deal. I need you to turn in question 6.32, 632 for the quiz today. Please put that on the desk there on your way out. Enjoy your spring break. Be safe. Don't bring back COVID. Stay outside as much. Enjoy it. And hope the weather's good for you all, wherever you may go. And I look forward to seeing you when you all return.